we will not be too late for lunch.
Thank you. Just it works. Good morning, everybody. So my name is Luciano Os, and I'm going to present to you the MAP platform, a multi-core, a NOC-based ARM processor platform. As we know, applications are getting more complex. We have nowadays applications with hundreds of billions of instruction code lines. And all those applications, they do need more performance. Basically, we need to deal with parallel processing inside of our systems. Taking that in account, we do know that the more cores we have inside, the more complex and challenges we have to face with and to deal with. And basically need to think about modeling, simulation, how to program such systems, and how to deal with the performance scalability as well. So what people are doing, they are adding more processing elements, cores, inside of the same system. They are duplicating or they are adding more processing elements inside of the same processor core or die, or they are replicating processing elements inside of the same system. So we can have those multi-core or multi-processing system on a chip. If you look at the literature, we have some academic platforms where we have some NOC-based multiprocessor system on a chip. Almost all of them, they do rely either on an old-fashioned processor or they do rely on an in-house operating system. In both cases, we lack in terms of we are not able to provide our students with something that can be useful or to allow them to use commercial tools and to learn a technology that is there. So that was the main aim that I had in order to propose and thanks to ARM, we were able to propose and to build up a platform that relies on both in a commercial processor and also in a well-known operating system that's FreeRTOS. So basically, as you can see, we do allow, so students, you'll be able, not only students, but researchers, to use our platform to considering Cortex M0 or Cortex M3 as their processor element. We can also, or are able, to set up a heterogeneous platform, so we can use both processors at the same time. We also, because as it has been mentioned before, the way that you allocate tasks in a multiprocessor system on a chip, they do impact on the reliability of its system, due to the power dissipation or the increased temperature on specific zones inside of your platform. So we also have on the top of our platform an extension of FreeRTOS. So basically, students will be able to play with different dynamic mapping algorithms, where basically you will be able to change a mapping algorithm and define different ways to allocate tasks on the top of those processing elements. The main idea of the platform is here. So basically, the platform is configurable, so you can set up the dimension that you decide. So basically, you can have on each processing element one of those two Cortex M processors, okay? And as you can see, inside of each processing element, we have a processor, a local memory, a router, a DMA, a network interface. We can also add other peripherals, like a ward or things like that. With this network interface, and this is quite important, it's AMBA compliant. So basically, I tend to say that we were able to remove the Cortex M3 and, for example, add or plug in a plug-and-play fashion way, the Cortex-M4, for example. And that tends to work straightforward. So here is the main idea of our platform, because basically I think if you want to bring the concepts and the reality of multiprocessor system on a chip, we should be able to provide our students with that kind of platform. And now we have this kind of platform, and our idea to distribute that along with the Arm University program. I'm going to explain how that's going to work. As you can see, our platform works in a distributed memory fashion way. So basically, it is scalable. So basically, the more processing elements to add, you can achieve a better performance. It relies on a cluster-based way. So basically, you can define some specific zones to execute a particular application. We have a research topic running at the moment where basically you are trying to define some secure zones on the top of this platform. So basically, you're going to allocate a given application to that specific zone, and then you're going to block. So any other message could pass through this secured zone. So this is ongoing research projects. So as you can see, we can use this platform for both, to teaching and also to develop research on the top of that. Each cluster will be managed by a local processing element that will be acting as a master, as a manager of that specific zone. And you can have multiple zones inside or define it on the fly on your own platform. We do consider that you have an application repository. So basically over there, you can add multiple kinds of applications, the object code organized as tasks. And then you can allocate them to a specific zones, as I had already mentioned it. As I just said as well, we can have on each processing element either the Cortex-M0 or the Cortex-M3. We have a local memory, and basically it has a dual port interface, so we can have simultaneous access from the network and from the processor as well. So we can receive a message and send messages through that, and read or write into it. We have a FreeRTOS running on the top of each processing element. You can decide to use the original distribute of FreeRTOS, or you can use our extension, and then you can have some other capabilities on the top of that. Our extension is non-intrusive, so basically we can use that. You can use a new version of FreeRTOS, and our extension will be useful there. We have done that for different distributions, and we can do that easily. So basically, you just have to add some, basically a file, and to add two system call functions, and that's going to work. So we have, like if you compare our distribution, we have supported dynamic mapping, as I have said before, and inside, in all those components, they are complied with AMBA protocol. Our router is based on Hermes NOC router. It's an academic router, and it's well known. Many research groups around the world, in France, in Germany, in Brazil, in UK, they are using this network on chip. It works, it has been used in different projects, and it basically relies on an X and Y addressing and routing algorithm. It also relies on packet switching and warm ROM and credit-based control flow. So basically you need to have a credit to send a packet or a fleet forward. And it takes 5 clock cycles to arbitrate and to rotate a packet from its input to the output of the router, okay? And each, inside of each router, we have input buffers to store fleets from each packet. So we can play with that, we can increase the dimension and the depth of this buffer on each input port of your router. And it has 5 ports, usually one of them is devoted to plug the processing element on its local port, like we call it. We rely on a structure of a packet that we can look at the NOC point of view and the kernel point of view, because at the kernel point of view, we see messages, not packets. Like inside of the network. Inside of the payload servers, we can add different things like data that is an object code from a task, or a data from a user, or from a kind of application that we are using for. The way that we have decided to model our applications, basically we do consider the input of our applications as a communicating task graph. So it's easy for students to understand that. It's also easy. We're basically going to define each task as a C code file. So basically you have a MJPEG code, you're going to have different tasks. In each task of each, you'll be a C code file that you have to compile later on. Easy. That should be easy for the students, basically. And that's the way, and people are doing that as well in different domains. We do rely on a NPI-like communication, message passing paradigm. So the way that tasks do communicate, they do send message and receive a message from each other. So that's the way that we have decided to do that. Since we have a system that is a distributed memory-based system. So that's the correct way to do that. Of course, that we could think later on to have locally, if you have a dual-core processor, for example, if you replace the Cortex M0 and M3, to have it locally, a different programming paradigm like OpenMP. So we can deal with parallelism on each processing element locally, but they will exchange data through a message passing paradigm. And that would be something interesting to play with later on, because you can have a hybrid parallel programming paradigm, and that's what usually happens in normal systems, HPC or system in reality. Here is just to show, because we are using our applications, they are modeled on the top of FreeRTOS, so this is a common way of tasks are considered in FreeRTOS. And here, basically, is how we play with the tasks that are intercommunication. We have, at the kernel level, at the application level, virtual buffers, where we do store messages that are exchanged through the tasks. Our communication layers, basically, is just to simplify how does it work. So this shows somehow how students will learn. There's a lot of concepts here, and they have to learn a lot of things. And my idea is to explore that this year with a MSc group, where basically I'll present them that, and I'm going to explain them all those layers, communication layers, and play with different concepts and ideas. So basically, we can come from the application level to the kernel level, the communication between the DMA that we have developed with the Cortex M0 or M3 processor, its intercommunication through the exchange of packets through the network on chip, and all the way through to the other task that will be allocated in a different processing element. So it's quite an interesting thing to play with, and that involves a lot of concepts, as I just have mentioned it. Our idea is to distribute a multi-level platform. So basically, we are going to distribute the same platform, the MAP platform, in 3 different levels. The first level relies on a virtual platform implementation. So basically, we are using Impera's processor models. So we have the same platform, we have a model of our network on chip, and we can execute the same software stack, the same kernel. So if you'd like to ask your students, for instance, oh, let's create a new application. So they will be able to do that faster using this virtual platform version. Then later on, they can go down and simulate that in RTL. And that you can execute the same kernel, the same software stack, and you can go down and simulate that in RTL. We do provide, with our platform, a set of scripts. So basically what you have to do, if you are a user, if you'd like to use our platform, we're going to provide you have to go to my website and download a set of files from MAP. Then you go to Arm University website, you download either the Cortex M0 or Cortex M3. You can go to FreeRTOS website, download its distribution. And basically you have to add those things on specific folders, and we do provide you with some automatic scripts. So basically you have to type, I want to execute a single core platform, a multi-core platform, and you can set up the size and the dimension of it, and voila, let's have fun. That's the idea. At the moment, we are working on FPGA distribution as well. Our idea is to provide you with the same platform running in FPGA. We have some initial results, and as we can see here, in a basically 2x2 configuration, only up to 60K, let's say, logical units are necessary to prototype it in a real FPGA. So that's the main idea. My idea is just to show the basic idea of the platform from a bird's eye view. If you would like to discuss more technically, you can contact me later on, and feel free to make questions. Those are the people who are involved in this project with me. As you can see, we are a small team, but we have done that quickly, I would say. So if you have questions, please, thank you for your time. Okay, no questions? Thank you very much.
What do you think is useful to include the FPGA visual at the end? What is the purpose of including the FPGA part?
It's because I believe when we are going to teach people, you have to engage students, and they have to see that working properly in a real platform, and that would be good. And also for research purposes, it will be faster to simulate things. To simulate a 2x2 platform, it takes, considering a simple producer and consumer application, that would take a few minutes to simulate that. But if you'd like to go further in a larger scenario, that can take hours or even days. Thank you very much for your time. No further question? Thank you for your question. Thank you for your time.
Yes, yeah, they told me we do.
You have the internet. No, no, you have it. Internet. Where is? Okay. Thank you, Protagoras. Okay. Last year, at the 2017 Arm Research Summit, a PhD student of mine and I presented here a demo in which we show how intensive neural processing can be performed using off-the-shelf small form factor FPGAs and PSOCs. That was possible mainly due to a wisely designed neural co-processing IP, which is part of the PhD thesis work of my student, Unai Martinez, who is sitting right there. Unai? Okay. And sometime later, we received the invitation of the Arm University program people to explore the possibility to develop a research enablement kit based on their CPU IPs together with our neural processing IPs. So here I am to explain you this project and in what point are we right now. Okay, the motivation, well, obviously the main motivation of the research enablement kits is to encourage researchers and university to use Arm CPUs on their system-on-chip research. But particularly, I think this research kit can attract many people from the machine learning application area to dare to experiment with machine learning or particularly neural processing system on chip from the processing point of view. So the main objective of this project is to provide researchers worldwide with a complete development framework for easily prototype system on chips based on Arm CPUs and on neural coprocessing IPs. And to do so, we are developing a platform to easy the downloading of some design tools and configuration tools of our IPs together with the IPs from Arm. So basically, the scheme of the project is this. On the one hand, Arm, through his DesignStart program, as you know, provide access to Cortex-M0 and Cortex-M3, and now we know to more CPU RTL, synthesizable RTL, and some EDA tooling and support and so on. And on the other hand, from the University of the Basque Country, we are developing a similar platform to provide researchers public access to our IPs and our configuration tools for those IP cores and some software scripts and drivers to easy the path of design and the validation of neural processing system on chip development. Generally, we call our neural processing IP ANA, or Artificial Neural Network Accelerator, but as you can see here, it's not just an IP core. It is a neural network IP core which is able to process any feed-forward artificial neural network model, but it is completed or accompanied by an interconnect IP, which we call MAI, or Matrix Aware Interconnect IP, and it is an interconnect to easy the integration of our IP core into a system-on-chip architecture. Basically, it provides like an abstraction layer for data accessing over distributed memory and heterogeneous memory, physical memory. It can be on-chip VRAM or distributed memory on the FPGA or even external DDR in a transparent manner. At the same time, this interconnect take the most of the available and usually limited on-chip memory because it provides a way for dynamic allocation of memory and so on. We are now developing other companion IPs. For example, we have now another pre-processing IP, which basically is a mean filter for video and image processing applications, which basically is a convolution layer for the classification of some video application associated. Well, the neural processing IP is basically fully configurable and scalable historic array of DSP blocks and associated VRAM blocks, which has been designed for efficiently compute vector matrix multiplication of products together with an optional function filtering layer, which will be the configurable activation functions of the internal or hidden layers of the neural networks. And well, it's a simplified scheme of the processor architecture is that it's worth to mention that this processor, the control path of the processor is tiny. I mean, because it has been designed to be a pure data flow processor, so the control path is just a few counters and signals. We have prototyped a couple of versions of the integration of this IP set into FPGAs and particularly into Silent Sync programmable circuits as well. To the left, there is the first version, the most simple one, which you can see the neural network IP itself together with the VRAM blocks and the matrix interconnect, which is provides a way to embed many different processing cores that have to have access coordinately to the same data set to be processed. So from in this first version, the ANA, or the neural network IP set, is just from the designer point of view is like a processing IP core which has an AXI interconnect interface. To the right, there is a more sophisticated prototype, which is basically the same, but we have added some an AXI DMA core and the previously mentioned convolution average filter IP. As you can see, we connect them in a multi-channel through a multi-channel AXI DMA, and this is very useful when your network models are very large, so the parameter set of the model cannot be embedded on internal memory, so the access to the external DDR is much faster. From the very beginning, we were aware that to make this IP set really usable, it had to be accompanied by a development tool which issues the path for the designer from the high-level setting of the network models to the synthesis of the IP cores and their integration into the system on chip. So my PhD student, Unai, at the same time, has been developing a prototype of a integration framework tool to automate all the process from the hyperparameter settings of the network models to the generation of this particular RTL for the synthesis of the cores, and there is an automatic tool for creating scripts and so on to easy the validation and the testing of the processor and so on. And if we have the time at the end of the presentation, he maybe can make you a short demonstration. To make the kit more attractive to the research community, we want to provide as well a preset, pre-integrated system on chip based on these IP cores. So we will provide the very same application example that we used last year, which is an on-chip real-time hyperspectral image neural classifier. As you may know, processing hyperspectral cubes is very demanding from the computational, from the processing point of view. So this is a good killer app for the acceleration of the neural classifier processor. And well, to the right you have some figures in these tables of particular implementation of the system, which corresponds to the first version of to the simplest one. As you can say, even using the no DMA version of the system on chip, we demonstrate that using small sync devices, for example, or small FPGAs, you can achieve real-time processing of the hyperspectral images, in this case, These are NASA's average spectrometer images, and this sensor has a maximum throughput of 12 frames per second. And in this particular implementation, we achieve more than 13 frames per second easily. But where are we exactly now? Well, now we can provide all these cores, the neural network processor, the companion interconnect IP, and some preprocessing IPs. Not all the configurability of these IPs are available in this moment, but they will be in the future. And we can provide as well this practical application demonstration of the integration of the cores with the ARM Cortex A9 into a thin device. What we are facing now is how to adapt the interfaces, the axis interfaces, to provide researchers with very similar options, but based on the very popular Cortex M0 and M3 for developing more IoT, low-power applications. And well, in the future, we'd like to continue developing the very wide possibilities of this design, providing more configurability in terms of more different neural models, for instance, multi-layer deep neural models, or even recurrent neural models, different computing precisions, applying more sophisticated methods for connection planning and so on, and maybe providing new IPs for signal pre and post-processing to be integrated together with this neural processor. At this moment, all these tools are not publicly available because the university is setting up a web service to provide public access to our tools and our IPs and the configuration tools and simulation scripts and so on. Unfortunately, the pace of the job is not as fast as we would like to be, but this is out of our reach. In any case, I think that for the end of the year, this can be available for the public. So, if we have a couple of minutes, Plutarchos, we can.
Just a couple of minutes.
Yeah.
It's longer than that, and we have to put it for the end of the session.
As you want.
A couple of minutes only?
Yeah, a couple of minutes. Yeah. It's just to see how the configuration tool works and what's the product we provide to be downloaded from the web.
No, ya está. Well,
in
let me just check.
And then it has a command line access, and it has also an embedded server, so it can be served as a web page with an interface. And because it's Golang, it can be compiled for either x86, so it can be used in a workstation, or it can put inside a sync device, which is running Ubuntu or any other Petal Linux or any other distribution, so you can run the configuration tool in the own chip before you actually use the design. The tool is meant to plug in different designs, so the designers or the administrators of the system can just write a plugin to add a new system to the tool, and then it's available for the user. And the input for the users is, as you see on the left, is just a JSON file with all the parameters that will be needed for the configuration. What is my? So in the top part, we just have the name of the system, which is the name of all the SOC integrating all the different tools. Then we have the synthesis parameters, and then we have all the parameters for each of the IP cores that are in the system. With this, we just call a command line tool, which is ana-gen generate, and we pass that JSON file with all the parameters. And it will directly take all the HDL source, it will change the parameters, it will generate a VUnit simulation script, it will generate precision synthesis scripts, and it will generate the Vivado project, where the output from synthesis can be directly put. So all the scripts are generated at once. Alternatively, instead of the command line tool, this would be the GUI to provide the parameters. It just loads a reference JSON, and then you can modify the reference JSON. Indeed, when this is available in the web page of the university, this would be the actual user interface for you to use. And then once it's generated, this would be the output. So you can see that here it's the HDL where are all the sources already parameterized and changed. We have the precision scripts, the Vivado script, the VUnit scripts, a copy of the configuration file in case you want to reproduce the same work later. And there's also a data folder, because all these IP cores are parameterized and they are also runtime configurable. So when you start the system, you need to pass some parameters to the IP cores to adapt them to the sizes of the networks you want to process. So these are given as CSV just seeds, or also as a binary arrays of data, so that you can directly put the binary in your ARM core and just use AXI to just flush the memory to the processor, and it's already set and ready to be used. And this is my 2 minutes.
Interesting what you show, but do you have any initial numbers of the performance of state-of-the-art accelerators? Because if you want to engage researchers to use your platform, some initial numbers would be nice, right?
Yeah, well, we are in the way of anyway, one of the strengths of this system, maybe I have not stressed it, is the super configurability of the IP core. I mean, as you can see, and this is a different approach from other IP cores. I see, because you can make a very specific design for a specific neural network model, and be very careful of how do you really control all data and so on. But as you know, there is no one-size-fits-all neural network model for any application. So the strength of this approach is that you can just define a high-level set of parameters, meaning how many layers do you want, how many neurons do you want per layer, what is the word length for the computation of the neural network, which activation function do you want at each layer, and so on. And you just click the button, and you get the processor. The processor is, I think, you get the processor, and you can define as well your hardware constraints in terms of how many DSPs or DSP blocks do you want to use in your FPGA. I mean, you can say, I want a two-layer with a two hidden layer neural network with 100 neurons in the first layer and 1,000 neurons in the second layer, and I only want to use 50 DSPs on my FPGA. And you push the button, and you get the processor that fits in with those constraints. So I think that's the strength of our approach. And in terms of throughput, it very much depends on this setting, because if you want a 1,000-layer neural network using just 50 DSPs, of course, you have to reuse many times the same DSP layer and so on. So the performance is not as much as if you would use 500 DSPs, for example. So it's difficult to compare with other proposals for accelerating neural networks.
Yeah, I see the strength of the platform.
Indeed, it's completely decoupled. I mean, when you want to synthesize it, you just say how many DSPs you want to use and what's the maximum memory you are going to use. And then you can fit any model without having to resynthesize and place and route again. So that's the main strong point, that you just synthesize once, and then you can use infinite number of network models as long as they fit in the VRAM you have allocated for the design.
Okay. So thank you.
Sorry, how much time do I have? It's okay, 15 minutes.
15 minutes,
Yeah.
it's going to be 1 o'clock.
Yeah, we're running a bit late.
Good afternoon, everybody. Can you hear me? Hello. Good afternoon. Professor Davis said that he stood between you and coffee, but I don't even stand between you and lunch because it's already lunchtime. I understand how serious that is, so if any one of you would like to sit down and leave and go for lunch, don't worry, I would not be offended. As you saw from the program, I come from Malaysia, so I'm going to transform you into a totally different world, because so far you've been hearing speakers and work and researchers from, the so-called well-developed countries, but this is the non-developed country, I would say. So I don't have bleeding-edge stuff to present. Maybe I will be telling you stories of what we try to do. Before that, very quickly, maybe it's pertinent for me to introduce myself. Most of you are up and coming already at the peak of your career, enjoying the peak of your career. But for me, I'm a 72-year-old man. I have retired for 12 years. I swear that I have enough of the corporate world. I used to work for AT&T Bell Labs. When I first started ASIC design, I draw transistors, individual transistors on a drawing board, a digitizing board. Okay, I designed stuff like the 7.4 series, 4-gate, 6-gate kind of ICs. And when I retired 12 years ago, we packed something like 60 million gates into a chip. So you can see, what generations of technology I've gone through and the design process, and also, in in the contribution to the tool development. Basically, synopsis and cadence came out of Bell Labs' design automation. I think that's enough. So after I retired, well, a little bit of the story. When I was working, and the reason why I retired was because I said I had enough of the stress. Believe me, ASIC is a very stressful work, all right? I had the responsibility of the entire Asia-Pacific region. So we have design centers in Singapore, Shanghai, Tokyo, Seoul, Shenzhen, all right? My biggest customers were Apple, Samsung, Seagate. All of them are more than 300 million a year revenue customers. And we brought up Huawei and ZTE, teach them how to do design. So you can imagine how stressful that was. And I swear, I said, I'm going to retire at 60 and not going to have any more of this stress. And I would, I have a plan. I said, I'll tour the world and I'll be playing golf every day. A new golf course every day. And I did exactly that. 2.5 months, I toured the entire USA, Canada, and the UK, hitting every golf course that anybody would want to be on their bucket list. And after 2.5 months, I went back. Well, I switched off my phone, of course, when I went on a golf course. But after I got back, now what, right? And when I turned on my phone, I started receiving calls, everybody calling me and said, look, we need you to help. We need you to help in this project. We need you to help in that project. I said, no, I'm retired, so don't call me. But after a while, I started thinking. I said, why do these people still want me, And then I come to the realization that, after being over 30 years in the industry and more than 10 generations of technology, there is some experience that I do have that, not many of my kinds still exist, especially now, because a lot of my peers, some of them are long gone. All right? So I said, no, I cannot be doing this. I cannot play golf every day. It's time for me to do something. And I started career as an academic with the University of Blair. So I said, the best thing is for me to now package all this experience and knowledge and contribute back and teach. So I went to Malaysia and contacted a few universities and says, I'm willing to do something, but it's on my terms. I will not take a single cent of salary, but you have to listen. Because when I went back to Malaysia, it was a sorry state of affair for the industry. They have 2 fabs, but there were no design capabilities. All right, so, my terms for the university is that you let me run a program. I designed the entire curriculum for VLSI design, undergrad as well as postgrad, and you just have to do what I say, right? And the first thing I instituted was nobody used any free tools. Sorry for people who develop tools in academic. Because from my experience in 30 years, when I hire somebody, it took me almost a year to train anybody to be proficient in turning the buttons. Just turning the buttons, understanding why they need to turn that button, all right? So I said that is, universities, the industry require us to produce graduates that can hit the road running, not spend another year going through another school, right? So I said, if they were to do anything in design, they have to learn the tools that are actually used in the industry. So I said, bite the bullet. We got 30 license or 36 license of Synopsys, front end to back end. Cadence, same, right? And of course, I negotiated with Synopsys and Cadence, and the license, the seats were almost given away for free. $3,000 seat. When I was in AT&T, we paid $200 million a year for license alone, right? Okay, now, so I had a planned program and said, this is what I'm going to take the universities through. But before I could do that, I said, if I were to just teach, there is no attraction, right? I don't know if you see this phenomena here, but in a lot of universities, it is extremely difficult to attract students to a technical education. The enrollment in science and engineering schools are declining year by year. And then if you want to introduce a program like VLSI design, they'll say, it's too tough, right? Let's do business administration or fintech or whatever you have right now, nowadays, right? So it's very tough. So what I decided to do was that, this was 12 years ago now. I said, okay, I have so many offers for a job. All right, I have so many offers to run startups and to do something. Why don't I take one of these? And one of my conditions to them then is if I take responsibility for your projects, then I want you to accept students that I bring. Right, those were my research students I'll bring, and you accept them, so that now they see that they have a direct link to their future career, right? And that's how I started. And then we started this program on doing multi-core SoCs. We launched this chip 2 years ago. All the good things that you heard, previous speakers talk about are all there, right? We built platforms. So it is well, we call this RUMs. We call this, we call the chip RUMs being the Raman University Multiprocessor System. I'm going to run through this very quickly. It consists of 4 M0 cores. These are some of the feature summary. I'm going to skip through this very quickly. It is easier if you look at this diagram. There are, is there a pointer here? No. I'm sorry, no pointer is working. You can see the 4 cores there. We have core 0, core 1, core 2, core 3. We have one core dedicated for I/O controls, and then we have this is kind of a semi-heterogeneous system, although they are all Arm M0 cores. But we have like an AES accelerator attached to 2 of them, and then a MAC attached to the 4th core, so that now we can use these specific functions, right? Encryption, DSP functions, and all that. Now, you must understand that when we took we took the DesignStart core. We started at the same time that Arm started the DesignStart program, 2013. So at that time, you have to admit, there was nothing, absolutely nothing. The RTL was an RTL for an FPGA, not for ASIC. There is no debugger, there is no bootloader, nothing. I don't know if you have it, but I saw earlier that now you're offering a host of stuff that we don't see. all right? And there's only one interface that we can talk to, and that is like, you know, response is like a week each time we ask a question. But we still took that RTL, we added all the stuff that is required for an ASIC, all right? And the additional stuff we added are all that outside of the inside square. We added a Utah adaptive NOC router. Right. We have to build all the testability features for the SRAMs and the flash. Right. We add a power management unit. Right. We have very low power LDO that stands by with 1 microamp of current consumption. So the entire system is built for IoT purposes, right? And I would say in my course curriculum, which has been adapted by the Arm University program, or adopted by the Arm University program, one of the module is a first-time success design methodology. Resonates very well with Professor Davis, right? Because coming from the industry, our pressure is if you're not first-time success with your design, you cannot afford to do that too many times. All right, so failure is not an option. That's our slogan. Right? And this design was taped out 2 years ago and was successful for the first time. Up to today, we have done many applications to prove in the device, and we have not changed one single transistor wiring. Okay, why were we able to do that? Well, these are some stuff, right? We have a team. I took in 2 research students each year, so you can see that this has gone through several years of development. My first student did the 4-core MPSoC with the Connect NOC router. Later, we have a second student which developed our own adaptive router. So he designed all those stuff, the AHP, the NOC bridge, the SMBs, the super patch controller, and test wrapper. The entire chip is completely testable by industry standards. So we either have BIS or we have scan. Yeah, we put in the power management, the debugger and bootloader and stuff. And then the second student built a platform for verification. And we use the UVM methodology with System C, not System C, but System Verilog for UVM, all right? He developed several UVC, universal verification components, which are all reusable, so that this platform is entirely scalable and configurable. So our first chip was 4-core, but you can use this platform for any number of cores. You can use 16, 32, 64, 1,000, 1024. The same platform can be used, right? And it's a verification platform. So you can apply the full UVM methodology to this and simulate with this platform. And then, okay, the next student builds the adaptive NOC router. Then the next students, now we are into, because dealing with SoC, you don't only talk about hardware. right? Hardware is no use if you don't have software to run it. So we built a platform for hardware, software, co-design, and co-verification at a very high level. Say we use TLM at the highest level. For the M0 core, we use the Imperas model, right? Which is a OVP model. So now at this level, because the model at that time don't exist for System Verilog, and System Verilog at that time do not support TLM. So we have to switch to System C, right? So which is a blessing in disguise, because now our group has capability in both System Verilog and System C. Now, if you're in the industry, you understand that this is not a small thing, because most outfit will only stick to one, either System C or System Verilog, right? And they're not straightforward stuff to use and proficiently, right? Right, so we have a platform for hardware and software co-design, co-verification. Before I leave this platform stuff, I would like to say one thing. There's all this platform, because we built it to be completely configurable and scalable. They can be used for architecture exploration in a very, very efficient manner. So, we're very flexible. We can put together, cobble together all kinds of different system architecture. And now, then a year later, our chip came out, right? We taped up the ROMs, and a year later it came out. And then now I have a student taking the chip and proving that it's actually not something just academic, right? It is a completely usable product. So we went to this wireless application space for IoT communication. We use the ROMs as a baseband processor. We basically try to emulate a very popular RF communication device called the LoRa, right? Long range, low power, long range. So because the LoRa codec is a proprietary codec, so nobody knows what's inside. And we went about trying to emulate that functionality or that feature capability. So what we did was we studied the modulation, technique, and also the coding decoding technique, the codecs. And we came up with a combination of BPSK and turbo coding implementation, okay? And we use, so we were very successful in demonstrating that we can use ROMs for this kind of application, which is, making use of the DSP capability and all the other cores in parallel processing and parallel task-oriented processing, right? This is the successful implementation of that LoRa-like transceiver features. We have the ROMs for one as a baseband processor, and we married that with a Line 602 RF transceiver, right? So the ROMs do all the baseband processing. It does receive data frame. It does encode the frame, and also the power shape and transmit, right? And on the receive side, then the ROMs do the receive synchronization, the code word decoding, and then the passcode framing, right? And this was successfully demonstrated very recently by another student, right? So now having done that, and our purpose for the RUMs, the 4 core RUMs, is in IoT applications. So now we have to really go into IoT. But before that, you know, as all of the previous speakers say, IoT, we have heard, without security is suicidal. Nobody would want it. So we went to, whoops. Do I have a slide on that? Oh, all right. Because time is running out, let me quickly say this, that currently our project is using the RUMs. We're building, again, a platform for an IoT system where we will enable the exploration of security features, right? So things like true random number generators are incorporated in the models, and we will have, you know, all kinds of facilities to investigate, you know, all kinds of side channel attacks scenarios, and then we have provision where we will invite attacks, and then you know, we can simulate at a very high level, at TLM level, the behavior of the security system. Okay, so industrial partners, they go with it. Because from the industry, whatever we do has to be all the good stuff, high performance, low power, everything. But there's one more important thing, is low cost, right? Especially with IoT devices, if you're not low cost, you can't afford it because you're gonna have lots and lots of these scattered all over the place. So I'm a cheap person. Low cost meaning cheap. So we implement all this at almost zero cost to the university, other than the postgrad scholarship to the students, right? I don't cost them any money. I negotiate with industrial partners, like Arm, for example, providing free DesignStart kits. I negotiated with Synopsys. Can you ever get a full suite of license from Synopsys for $3,000? I don't think you've ever heard of that, right? And we got 36 licenses at $3,000 each. Don't tell Synopsys I told you this, though. Same thing with Cadence, and then also with the SSD Superflash. What else? Yeah, Celtera is a fab in Malaysia that provides us with free MBW. Right? So almost everything is free, or at a minimum cost. So a little bit of advertisement for them. And well, current project and future projects, we'll skip over that because it's lunchtime for you. So thank you very much. And if you would like to communicate with me, here's my contact. And I'm on WhatsApp. Oh, one more thing. You know, I got not only resistance from a lot of people, I get resistance from the academic community as well. I invited a lot of them to come join my program and take part in this. You know, one of the things that they say, and I don't know if you guys have ever heard this, is, why do I want to do VLSI design? It's so difficult to publish. You know, academic, everything has to be published, right? They say, I can't get any publication now. I said, this is the proof. All these, although some of them are conference papers, all these are IEEE peer-reviewed, properly archived papers, right? So we have all this as publication in a few years that we're in this program. Right, thank you very much. Bye-bye. Question or lunch?
So, for your demonstrations where you used the RUMS chips, like to reverse engineer the communications protocol. Oh, sorry. Yeah. So, for your examples where you were. Sorry. Thanks. So, for your examples where you were reverse engineering the communications protocol using the RUMS chip, how much did you use the 4 cores, or were the software just running on 1 core? What kind of mechanism did you use to program and run in the multi-core environment?
Okay. Yes, that's a good question, because we do not implement any OS, not even RTOS. So they are all machine coded for a start. I mean, we have to do a quick and dirty one, right? So they're all machine coded. The tasks are all allocated manually. And we have of course, after allocating tasks, I mean, it's a experimental, right? It's a trial and error approach. So we allocate a different task, and then we see the performance, and then we adjust, all manually. So it's a quick and dirty proof that the chip works, but of course we can put in RTOS and OS in there, right?
So I guess the question is, you had a little NOC communication fabric on the RUMS. Have you ever actually used it yet? I mean, it certainly is.
Oh, it's used because the cores, you know, especially the turbo coding is an iterative loop, right? So it's like, you know, every iteration you finish your task, then you pass your results to the next core to continue for that core to continue with their task. It's a task-centric allocation, right? So a lot of message passing going on. Thank you. Thank you.
Thank you very much for attending, and enjoy your lunch now, if there is time.